Welcome to webinar on rotating machinery vibration due to unbalance and correction methods.
Greetings to everyone. I'm Kishore Kumar Aguna. I have 10 plus years industrial experience and worked in various mechanical engineering disciplines such as NDT, welding inspection, and condition monitoring. As of now, I am working independently and associated with the various organizations involved in testing, commissioning, and planning, reliability, and maintenance. I would like to share my experience and prepared notes on various reliability and maintenance topics from various books, articles, videos from internet. This presentation is prepared on rotating machinery vibration due to unbalance and its various techniques and solutions practicing in an institute to solve unbalanced vibration.
Unbalance. Rotor unbalance is the most common malfunction in rotating machinery. It is so widespread that, if any lateral vibration occurs in the rotor, there exists a tendency to associate it with unbalances. By definition, a rotor has an axis of rotation. A rotor has a mass axis which passes through its center of mass, often called center of gravity. Due to manufacturing errors and material variations, the mass center does not line up with the geometric center. Tolerances are the definition of how much error is allowed. Unbalanced sources. Rotor unbalance is a condition of uneven mass distribution in the radial directions at each axial section of the rotor. In an unbalanced condition, the rotor mass center line does not coincide with the axis of rotation. Unbalance can result from rotor material non-homogeneity such as voids, porosity, inclusion, etc. Specific types of imperfections in design, fabrication, and assembly can also cause unbalance. Unbalance may also occur during machine operation due to erosion or buildup of deposits in the rotor, missing or loose rotor parts, or load-related and/or thermal distortion of the rotor. The unbalance may also occur due to a rotor crack. In some machines like centrifuges, the unbalanced state is directly associated with their main function. In fluid handling machines, unbalance can be developed due to distorted fluid flow. During rotation, the rotor unbalance generates a centrifugal force perpendicular to the axis of rotation. This force excites rotor lateral vibration called rotor fundamental response, unbalance, and centrifugal force. There is a precise mathematical relationship between unbalanced speed and centrifugal force. Centrifugal force due to unbalance is directly proportional to the product of amount of unbalance and square of rotating speed of the rotor. Two things are important to remember. 1. The force is proportional to the unbalance. 2. The force is proportional to the square of the speed, unbalance, and speed. Many people think that unbalance gets worse as speed increases. We know that this is not the case. Unbalance is a constant, it is a mass property of the rotor. If a rotor with zero unbalance is run at any speed, there will be no vibration or bearing forces. This is a theoretical situation only, of course. As speed increases, vibration velocity increases in direct proportion. Velocity is displacement multiplied by frequency. The eccentricity, displacement, is a constant, while the frequency increases. Centrifugal force follows a square law relationship since it is the rate of change of velocity equals velocity times frequency. Unbalanced type, static unbalance. Static unbalance is a condition of unbalance where the central principal axis is displaced parallel to the rotating center line. It can be detected by placing the rotor at its point of rotation on each end. The heavy side of the rotor will swing to the bottom. A part is considered statically balanced when it does not rotate regardless of the position in which it is placed. Static unbalance can be corrected by adding or removing weight in only one correction plane. Unbalanced type, couple unbalance. Couple unbalance exists when two unbalances exist 180 degrees apart, but in different planes. This condition of unbalance has a central principal mass axis intersecting the rotating center line. Unlike static unbalance, couple unbalance cannot be detected by allowing the rotor to spin freely. Correction of couple unbalance requires that weight be added or subtracted within two correction planes. In only very few cases will a rotor have true static or true couple unbalance. Normally, an unbalanced rotor will have some of each type. Combinations of static and couple unbalance are further classified as quasi-static or dynamic unbalance. In fact, during the process of static balancing, one can add a weight in the wrong plane, as seen in the methods of fixing static unbalance. When the weight is added disproportionately, a coupled unbalance is created. Couple unbalance can only be detected when the part is rotating and can be identified by comparing the bearing or shaft vibration amplitude and phase readings at each end of the rotor. Readings from a rotor experiencing couple unbalance will reveal equal amplitudes of vibration with phase readings which differ by 180 degrees. Again, this method of detecting the type of unbalance does not apply to overhung rotors, unbalanced type, dynamic unbalance. Dynamic unbalance is the most common type of unbalance and is defined simply as unbalance where the central principal axis and rotating center line do not coincide or touch. This type of unbalance exists whenever static and couple unbalance are present, but where the static unbalance is not in direct line with either couple component. As a result, the central principal axis is both tilted and displaced from the rotating center line. Generally, a condition of dynamic unbalance will reveal comparative phase readings which are neither the same nor directly opposite one another. This type of unbalance can only be solved by making weight corrections in a minimum of two planes. Unbalanced type, quasi-state unbalance. Quasi-static unbalance is the condition of unbalance where the center of rotation intersects the element's geometric center line, but not at its center of gravity. Quasi-static unbalance can be detected by the amplitudes of the vibration being very different at each end of the shaft, and being out of phase by approximately 180 degrees. Once again, this type of unbalance must be corrected in two or more planes. Quasi-static unbalance is very common on motor pulley combinations where the motor is balanced, but the pulley is unbalanced. It can be corrected with the single correction weight on the plane of pulley, single plane balancing. Quasi-static unbalance could be considered as an impure static unbalance. Even though it is a single plane unbalance, it causes a dynamic effect with both static and a couple components. Rotor rigidity characteristics. There are a number of classifications of rotors, depending on flexibility, operating speed, and other factors. ISO 5343. Class 1 is rigid rotors. This covers 90% of all applications. Class 2 is rotors that are not rigid or that have special characteristics of mass distribution but that can be balanced using a modified balancing technique. Choice of correction planes is the key here. Classes 3 and 4 are flexible rotors. We mention this so that you are made aware that some rotors may have to be balanced at specific speeds, at 2 speeds, or even when hot. Thermal effects can cause distortion that in turn causes unbalance, which can cause more distortion. 120 The balancing process. Some call this type of operation dynamic straightening rather than balancing since the aim is to keep the rotor running true by minimizing internal bending stresses of the rotor. Unbalanced vibration spectrum. Vibration due to unbalance occurs at a frequency of 1 times RPM of the unbalanced element, and its amplitude is proportional to the amount of unbalance. Normally, the vibration signal is measured in both the vertical and horizontal planes. With the simply supported rotating element, that is a bearing at both ends of the shaft, the vibration due to unbalance will be in the radial plane with very little vibration sent in the axial direction. In the case of an overhung rotor, high axial vibrations may occur, and the amplitude in the axial plane may equal those measured radially. The spectrum for unbalance. Force unbalance will be in phase and steady. Amplitude due to unbalance will increase by the square of speed below first rotor critical. 1x RPM is always present and normally dominates spectrum. Also, approximately 90+/30 degrees phase difference between horizontal and vertical readings usually occurs on each bearing of unbalanced rotor. We need to remind some characteristics. while diagnosing what kind of unbalanced condition present in rotor. Static unbalance characteristics. Spectrum, high 1x in the radial directions, low in the axial direction. Waveform, the waveform will be very sinusoidal when viewed in units of velocity. If it is not sinusoidal, then there may also be misalignment, cocked bearing, a bent shaft, or some other fault condition. Amplitude, compare vertical to horizontal vibration on a horizontal machine. If horizontal 2x vertical amplitude, then suspect foundation looseness or resonance. Phase, look for 90 degrees phase shift between vertical and horizontal. For pure static unbalance, phase at bearings at either end of the rotor will be in phase. Couple unbalance characteristics. Spectrum, high 1x in the radial directions, low in the axial direction. Waveform, the waveform will be very sinusoidal when viewed in velocity. If it is not sinusoidal, then there may also be misalignment, cocked bearing, or some other fault condition. Amplitude, compare vertical to horizontal vibration on a horizontal machine. If horizontal 2x vertical amplitude, then suspect looseness or resonance. Phase, look for 90 degrees phase shift between vertical and horizontal. For pure couple unbalance, phase at bearings at either end of the rotor will be 180 degrees out of phase. Dynamic unbalance characteristics. Spectrum, high 1x in the radial directions, low in the axial direction. Waveform, the waveform should be very sinusoidal, if not there may also be misalignment, looseness, or other fault condition in addition to unbalance. View in units of velocity if possible. Phase, phase is the best indicator. Look for 90 degrees phase shift between vertical and horizontal. Phase at bearings at either end of the rotor will be between 30 degrees and 150 degrees out of phase. See also static and couple unbalance, rotor balancing. The ISO 1925, paragraph 3.1. Definition of balancing is a procedure by which the mass distribution of a rotor is checked and, if necessary, adjusted in order to ensure that the vibration of the journals and/or forces on the bearings at a frequency corresponding to service speed are within specified limits. Note the progression, check against, limit, adjust if required. Note also the important phrase corresponding to service speed. Balancing cannot fix vibration at other frequencies than the rotational, the right balancing tolerance. In order to help with determining tolerances, standards such as ISO 1940 were developed. This ISO is based on the measurement of machinery vibration velocity. The ANSI spec is identical but printed by American National Standards Institute. The API specification is written around pump requirements in the petrochemical industries and classifies unbalanced levels as a function of rotor mass and operating speed. ARP documents are built around the requirements of aircraft engines. ISO 1940 standard recommended balance tolerance. ISO 1940 is famous for its classification of vibration in terms of G codes. Although many people don't know what they mean, it is easy to figure out that G2.5 is a tighter tolerance than G6.3. Notice the choice of words here, tighter not necessarily better. G2.5 means a vibration velocity of 2.5 mm per second under specified conditions. Unfortunately, it is the theoretical value assuming the rotor was spinning in free space, so it does not relate to actual operating conditions. Using ISO 1940, balance tolerance is equal to product of 9.54, G number and mass is divided by RPM, API 610 standard recommended balance tolerance. API 610 is based on a very simple formula. T is equal to product of force and weight divided by speed. A simple formula does not guarantee easy balancing. For high speed pumps, especially, the tolerance can get ridiculously tight. When the tolerance is below 20% of the diameter tolerance of the bore, it can be classed as ridiculous. Balance quality, the importance of angle. If there is one problem in balancing that appears minor, but has major effects, it is angle error. It is usually easy to see when an unbalanced correction is too small, the unbalanced amount reduces and the angle stays the same. If the correction is too large, then there is a 180-degree phase change. When there is an angle error, the amount may be overcorrected or undercorrected, but there is a major angle change that generates confusion. Often the operator will complain that he is chasing the unbalance. After unbalance correction, the amount is slightly reduced, but the angle is very different. We have to remember that unbalance is a vector quantity, and that means we have to know what balance quality, phase error. This may not be immediately obvious, but the actual amount of correction was very close to perfect. The proper amount of material was removed. However, it was removed at the wrong angle. We have to look at the dreaded trigonometry and evaluate the sine and cosine. For the angle error of 10 degrees, the cosine of the angle gives us the error in correction amount due to the angle error. The correction was less effective due to the error. The sine of the angle error gives us the value of the error at 90 degrees to the correction. This is a new unbalance generated by making the correction at the wrong angle, balance quality, phase shift. If the correction was within the 5–10% error we normally expect with amount, and due to normal error is things like drill depth, weighing error, etc., what this does is raise the angle change to more than 90 degrees. If we had made an undercorrection, the angle change would have been less than 90 degrees. With an accurate correction, we would expect the unbalance to drop by a factor of 10 due to normal measuring and correction errors. If the angle is not calibrated correctly, then the errors are much greater. Balance quality, correction efficiency. With a system that is working well and has the capability of calibrated correction, for example drilling or adding weights, we expect to reduce the unbalance by a factor of about 10 to 1 in one shot. The initial unbalance U is assumed to be a point, but if we make a second measurement, the value would change slightly. After correction, the unbalance should be within the dark circle. Larger percentage errors are likely when working to very tight tolerances, balancing at very low speed, or when there are other problems. This can make it hard to determine the real problem. Actually, the first step is to improve repeatability. This may mean calibrating the angle with a larger unbalance to give smaller percentage errors. If we have an angle error, photocell moves, for example, we will have that 10% residual shifted by the sine of the error angle. This would put the residual unbalance within the white circle. If correction is made by non-calibrated method, hand grinding, for example, the correction error will be larger and the effects of the angle error will be harder to identify. Balance quality, unbalance vector. With a precise unbalance amount correction, the residual unbalance is due to the correction being made as the wrong angle. The amount of the error is directly related to the angle error, or more precisely to the sine of the angle error. An angle shift of less than 90 degrees means that the unbalance was undercorrected. When the angle shifts by more than 90 degrees, it means that the unbalance amount was overcorrected. There is a direct relationship between angle error and the effect of angle error reflected in the residual unbalance amount. At 10 degrees the amount error is 2%, which is still small compared to an error of more than 17% due to the 10-degree angle error. Angle errors of less than 3 degrees are acceptable for most applications. Balance quality, correction ratio. Correction ratio is very important when the initial unbalance is high, more than 5 times tolerance. This is simply the ratio between the initial unbalance and the final unbalance after a single correction. With the well-adjusted measuring station and correction system, it is normal to be able to achieve a correction ratio of 10 to 1 when initial unbalance is high, 5 tolerance or more. If the initial unbalance is high, and there is enough material available to add or remove, the correction ratio can be much higher than this. When initial unbalance is low, the percentage variations in the readings will be higher and the correction ratio will be lower. This does not matter if the rotors still come within tolerance after one correction. Balance quality, trial weights and force. Care should be exercised in the selection of the proper trial weight size. If it is too small, no change in phase or amplitude may be noted, and one trial run will have been wasted. If the trial weight is too large, it could cause damage to the machine, especially if it normally operates above the first critical speed. As a general rule, a trial weight should be selected that will cause a 30% change in amplitude or a 30-degree shift in the reference mark location. Changes of this magnitude will ensure accurate results are obtained from your calculations. A common practice used in selecting the size of a trial weight is selecting a mass that will produce a force equal to 10% of the rotor weight on the supporting bearings, balance quality, balancing planes. As a general guide, rotors with the WD ratio of 0.5 or less may be balanced using the single plane method if they operate at less than 1,000 revolutions per minute. Above 1,000 RMP, the two-plane method should be used. Rotors with the WD ratio above 0.5 that operate below 150 revolutions per minute may use the single-plane method of balancing. Those above 150 revolutions per minute should use the two-plane method. Overhung rotors are often found in fans or blowers that have a WD ratio of less than 0.5, and most often operate at speeds of less than 1,000 revolutions per minute. The single-plane method of balancing can often be employed to correct unbalanced conditions for this type of rotor. Workshop rotor balancing. A balancing machine is a complex measuring instrument combined with mechanical drive components and rotor support components. It measures to accuracy equivalent to that of a high-quality coordinate measuring machine, CMM, and does so in shop conditions rather than those of a quality control laboratory. Balancing machines themselves are classified by 4 basic criteria. Horizontal or vertical orientation of the rotor axis. 2. Soft bearing or hard bearing. 3. Single or two-plane. 4. Single-plane balancers. Workshop rotor balancing. Horizontal or vertical orientation of the rotor axis. Most horizontal balancers are used for rotors that have integral bearing journals that fit directly to the roller bearings of the machine supports. After balancing, a rotor can be removed from the machine, be replaced later and give virtually identical results. Vertical balancers, and some horizontal machines, have a precision spindle as part of the machine. This provides a mounting location for rotor-specific tooling. The rotors that get balanced on these machines do not have integral bearings, and so the rotor must be mounted on some type of tooling. Most horizontal balancers are used for rotors that have integral bearing journals that fit directly to the roller bearings of the machine supports. After balancing, a rotor can be removed from the machine, be replaced later and give virtually identical results. Vertical balancers, and some horizontal machines, have a precision spindle as part of the machine. This provides a mounting location for rotor-specific tooling. The rotors that get balanced on these machines do not have integral bearings, and so the rotor must be mounted on some type of tooling. Workshop rotor balancing, soft bearing or hard bearing. Soft bearing machines normally have a lighter construction and may have a lower purchase price but have to be calibrated for each rotor and each balancing speed. Hard bearing machines are permanently calibrated, which makes for quicker setup and better performance with larger rotors, high drive powers and high windage loads. Due to the heavier construction and increased need for a good foundation, the initial cost of a hard bearing machine is usually higher than that of a soft bearing machine, especially with larger machine sizes. The hard bearing machine pays for itself with shorter setup times, lower balancing speeds. Workshop rotor balancing, single or two-plane. Static or dynamic, single-plane balancers are usually vertical spindle machines. This is the ideal machine for disc-shaped rotors with no shaft, such as brake discs, flywheels and pump impellers. When we are dealing with high-speed rotors such as those in small turbine engines, the operating speed can be in the range of 50,000 revolutions per minute. Even very thin rotors can require two-plane balancing to very high tolerances. Related to this may be requirements for trim balancing assemblies of several rotors to ensure the engine performance is to specification. Most two-plane machines have the capability to be set up for single-plane balancing. Narrow rotors only require single-plane balancing. A narrow rotor is generally okay for single-plane balancing when its diameter is more than 3 times its width. We would also consider the distance between the bearings in service condition, workshop rotor balancing. Single plane balancers. Further classified as rotating or non-rotating, centrifugal and gravitational. Non-rotating machines are normally used for high-volume production of rotors with coarse balance tolerances such as automobile brake drums. Cycle time is short as no acceleration and deceleration, and the tooling does not have to clamp the rotor, just locate it. The lack of centrifugal force to amplify the effect of the unbalance makes these machines suitable for rotors with relatively coarse tolerance. The additional requirement for short cycle times and simple tooling further makes the case for this type of machine in certain applications. In-place balancing. One additional type of balance equipment is the portable balancer. Some situations require trim balancing in the final operating location. In operation, erosion and dirt buildup change the unbalance, so frequent rebalancing in the field is required to maintain performance. High-speed rotors may need to be trim balanced due to thermal and multiple bearing interactions. This is a subject for an advanced course. Centrifugal pumps may have hydraulic unbalance. The mass of fluid and uneven passages changes the unbalanced condition. This can only be fixed by trim balancing with measurements made under normal operating conditions. A portable balancer comprises vibration pickup, zero-phase reference, and an instrumentation package. A calibration routine is used to calibrate the system for each specific rotor. Two-plane balancing is often practical, but in some cases the rotor configuration does not lend itself well to consistent plane separation. In-place balancing. Procedures and pitfalls. In-place balancing is not so simple. The pickups typically measure a noisy signal, and there may be high vibration signals with low unbalance. Noise can come from other machines, bad bearings, loose mounting, worn driveshaft, or damaged drive belt, gear noise, and many other causes. In order to evaluate if balance is a problem, the first step should be to check the total vibration. If this is low enough, no action is required. If vibration is too high, then adding a synchronous filter to the system will indicate what percentage of the vibration is at running speed. If the filtered signal is significantly lower than the total vibration, then the problem is probably not unbalanced. If the filtered and unfiltered values are similar, then unbalance is a probable cause. Attempting balance will soon reveal this. If the rotor does not respond to balancing attempts, the next step is to check for other causes such as misalignment, and maybe move the pickup from horizontal to vertical orientation to determine if it is a structural problem. In short, using portable balancing equipment is much more dependent on experience and diagnosis than shop balancing. Results are unpredictable. Keeping good records of each action and following careful procedures will help avoid frustration and loss of confidence and credibility later. Rotor assemblies with gearboxes have multiple speeds and factors such as coupling alignment, bearing noise, gear noise, and the equipment operation each produce characteristic vibrations. These have to be investigated and eliminated before balancing will be effective. Active balancing. Sometimes there is an unbalanced problem that does not respond well to either the use of a balancing machine to in-place balancing. One example of this would be high production grinding operations. The grinding wheels are large and fragile and run with continuous application of coolant. As the wheel wears, a diamond tool is used to true and reshape the wheel. After a few hours of operation, the wheel has developed unbalance. Stopping the wheel, removing it from the machine, balancing and reassembly is not practical since there is the possibility of damage. There will be new runout from the assembly tolerances and the coolant drains to the bottom of the wheel, making it impossible to obtain a correct unbalance reading. The solution is to add the balancing operation to the grinding machine. This requires the addition of suitable vibration sensors, a balance correction ring that can be modified with the wheel running, and a control system. Today's active balancing systems are used on fans, turbines, pumps, machine tools, and many other applications where maintaining accurate balance can eliminate costly premature shutdown or loss of performance. Single plane balancing. 4-run method. To perform a 4-run balancing procedure, one only needs a means to measure vibration amplitude and use polar graph paper. 1. With the machine in operation, locate and measure the point of highest vibration on a bearing. Either attach the pickup to this position or accurately mark its location so subsequent measurements may be taken from exactly the same place. 2. Measure and record the vibration amplitude. 3. Place a trial weight at some location on the rotor, restart the machine, and record vibration amplitude T. 4. Stop the machine, rotate the trial weight 90 degrees to 120 degrees as most convenient at a constant radius, restart the machine, and record vibration amplitude T2. 5. Stop the machine, rotate the trial weight another 90 degrees to 120 degrees in the same direction at the same radius, restart the machine, and record vibration amplitude T3. The correct weight addition may now be calculated from the formula, trial weight multiplied by division of final run reading to initial run, single plane balancing. A vector approach to single plane balancing. 1. At running speed measure the amplitude and phase at 1x RPM. This is plotted as the O vector. 2. Shut down the machine and add a trial weight of a known amount. Trial weight. 3. Run the machine and record the new amplitude and phase. A rule of thumb is look for either a 30-degree phase change or a 30% change in amplitude. This vector is plotted as O plus T. 4. Connect the end of the O vector to the end of the O plus T vector and label this as T. 5. Measure T. 6. Use the formula correction weight equals trial weight x OT. 7. Measure the angle between O and T with the protractor. 8. The goal is to adjust vector T so it is equivalent opposite vector O. 9. Remove the trial weight and add a correction weight. Advanced balancing methods. The newest multi-plane balancing techniques owe their success to advancement in these areas. Orbital balancing. This procedure is based on the observation of the orbital movement of the shaft centerline. 3 signal pickups are employed, of which 2 probes measure the vibration amplitudes of the rotor in 2 mutually perpendicular directions. These 2 signals trace the orbit of the shaft centerline. The 3rd probe is used to register the once per revolution reference point and is called the key phasor. In the orbital method, the damping is not taken into account. Therefore, in reality, this method is effective only for very lightly damped systems. Modal balancing. Modal balancing is based on the fact that a flexible rotor may be balanced by eliminating the effect of the unbalanced distribution in a mode-by-mode sequence. In many discussions on modal balancing, fluid film damping is not included. In other instances, rolling element bearing effects are neglected. In such cases, the practical usefulness of the modal method is not fully defined. Multi-plane balancing, influence coefficient method. Modal balancing came into being to alleviate the problems of the supercritical rotor unbalance of the steam turbine generator industry. It combined the then available techniques for calculating response amplitudes for the various rotor vibrational modes with the available instruments for measuring actual installed vibration levels. In recent years, more systems have been designed for supercritical operation, advanced in situ balancing tools. Newer types of sensors and instruments are becoming available, making it feasible to obtain precision in amplitude and phase measurement. Many computers for operation on the shop floor or in balancing pits, and time-sharing terminals for in-the-field access to large computers, are now commonly available.
I strongly believe power is gained by sharing knowledge, not hoarding it. I would like to thank each and every person who shared their views and knowledge from their books, articles, and internet. Without them, it's not possible to make this presentation and to earn my everyday bread and butter. From the beginning of human race, find how to use stone as a hunting tool, use fire and wheel. Every generation has passed their knowledge and led us where we are now. I hope you enjoyed this presentation. Namaste. Thank you for your attention. Please share your valuable suggestions and feedback to my email isagna@gmail.com.